boundary layer, then you cannot apply these equations if you are in that regime, if you are in that spatial region. So let's do one example. It's I think example 3.1. In some books it might be some other units, but let's get the idea across. Consider it as this one as well. If we are unable to complete it, at least you get the idea what is happening. So it says that consider inviscid, incompressible, steady flow. So if we consider this, what automatically qualifies? The three conditions are satisfied right away in one sentence, right? So the way it is written is that this is this, and the streamlines are coming and they are following this path, and we have this x and y direction, and the way he suggests is that the velocity is in fact v naught 1 plus a cube over x cube. Now the radius is a, okay, and this part we will cover maybe by the time we are in chapter 6. We will derive these equations in a very different way, but that's the thing which gives us how the velocity varies as we change the value of x. A is a constant, it's just a circle with a radius a. Let's say a is 1, so you already know what is that number. So the point here is that you have your origin somewhere here, right? So this is the origin, and by the way he calls this as z, so let's keep the same convention. Rather, it's the origin is here, and the way the velocity comes in is v naught, which is v naught. Okay, so give me the velocity at this point. How do you know that? What is the value of x? What is x? So what is the velocity here? And let's say give me the velocity at let's say this is minus 3 times a. Give me that number. What kind of number are you generally thinking? Positive, negative? Positive. It's a positive number. And x cube is, cube means if it is minus, this is a minus, it's a negative number. A cancels out, so you have minus 1 over 27. So 1 minus 1 over 27. So 1 over 27 is really a kind of a small number. Over 90%, right? So 1 minus 0.9495. Okay, so that part is 0.95 V naught. Okay, so that means, sorry, 0.96. So that means that even it has not reached the structure cylinder, it has started to slow down. Give me once x is minus infinity. So V is, so that means we are so far from this this structure that our velocities still remains same, right? Excuse me. So as we approach or we get close to it, it starts to sense that there is a body up there. And this thing we covered, I think, chapter 1, where we were saying that the disturbance, it also travels at the speed of sound. So that means the body which is going to come, which is still ahead, has sent some sort of disturbance which generally travels with the speed of sound. So the velocity would automatically adjust itself. If I am moving more than the speed of sound, then I'll go and crash in that body, and then I'll realize that, oh, there was a body up there, right? So that is why you have shocks. That shock wave is generated because of the fact that the particles in front, they have no clue that something is coming, and there is a big variation between the pressures, between the densities, between the temperatures, right at a very small distance. So that variation is so quick that we call that there is a shock wave here. But in this case, it is quite smooth, and we can come up with this these numbers, that as we are getting close, the velocity is kind of decreasing, and ultimately it comes to this one. So what is the value if, let's say, can I give, so for this one, this particle which is moving, S is in fact X direction, right? Can I say that the streamline is along X direction? So S is X direction basically. So if I have to find this is the same as this, which is, now give me this. Okay, good. Right, and in our governing equation we have, okay, so if this is this means that the velocity varies in X direction using this law. When is the velocity maximum? This quantity is maximum. What happens? It goes to 0. What does that mean? That you are so far that as you are changing in X direction, the velocity is not changing. But as you come close to the cylinder, the variation in the velocity in X direction, that number is high. So we call this as, what does that mean? Right. Right. What did I say? Did I say the other way? So the point is, if you are very far, X is like, say, 100 times A in minus 100, so it is still kind of V0. Even it is minus 58, it is still kind of V0. So in the X direction, the velocity variation is not high. So partial V, partial X is almost 0. But as you grow, as you come very, very close to the structure, the change in velocity is huge, because from V0 it has to go to 0 in a very short span of time, and in a very short span of distance. So those gradients are high. This partial V, partial X means this. Okay, now let's use the Bernoulli effect. Partial P, partial S was there is no change in Z direction. It's just the streamline which we are following is the straight line. It's not moving in Z. So let's equate this term. What do we get? Now this term becomes what? we said this is minus what is 3, what was that? So we have a V naught here, and this V is already given, which is what?
So is equal to V naught into 1 plus A cube by X cube. So V naught square.
Right, so we have another V naught, which I write this, and then somewhere we have a rho as well, minus rho, so this becomes a positive?
Negative.
Still negative?
Positive.
So what does this becomes? Let's say now we are looking at, what is this final one? Let's write it a little neat. 3 rho A cube okay. So now what, okay, one important thing is that whenever we talk of pressures, I think I mentioned it before as well, whenever we talk of pressure, the most important thing is the pressure differential. As an engineer, that is something we are always looking for. If somebody says P is 50 penny unit, who cares? Till the time there is a pressure differential, you don't see the let's say the flow moving. If there is a pressure variation, then that one is important. Flow past a wing, low pressure on the top, high pressure at the bottom, there is a pressure differential that causes lift. Absolute value of pressure is not significant for us to know. We are generally interested in how much is the pressure difference. If it is less than atmospheric pressure or towards vacuum, the flow would, let's say, flow inside. If it is more than that, it would follow towards the atmospheric outlet. So pressure differential is the important thing. Okay, now there's a plot in the book, and you can use any mathematical software if you really want to plot it. The way it is plotted, let's do that way. And this is X, and I am plotting this. Since we are analyzing only in this direction, which is, let's say, minus A, cylinder is somewhere here, this is that. So you will see that the pressure is something like this. Suddenly it goes up and then drops to this. By the way, it drops straight, but look at the book, it has a better figure. I could not draw it well. So the point here is there is a peak pressure just before it drops down to 0. And the velocity here is can somebody explain, if partial P partial X is 0 here, is there a pressure here? Sorry? Pressure is 0, 1, 10, 100, what? Okay, so we have again this structure here. Now I want to plot the pressure. Again, it would start low and it will end up high. And this number is half rho v squared. There is some differentiation between the types of pressure as well. which I think we'll cover later, is something is known as a static pressure and something known as a dynamic pressure. I can give you an example from the aircraft. You have these things, crazy aircraft sometimes, and then with the wing there is something, in olden times especially, there is something known as a pitot tube. So that is exactly the same as this cylinder part, which is kind of, the particle comes in and hits and stops. Hits and stops. Which one?
0.5
Oh, from this equation. We have to integrate and then we get it. It's a little procedure given in the book. I can, okay, let me write. If you integrate, then this. This physically is the same thing as you were talking. Something like this, a crazy kind of. F(x) is minus a, then things go down, but like kinetic energy, and then you have potential energy. Right, conservation. But the point I was emphasizing was there are different types of pressures. Static pressure, dynamic pressure, we'll talk about next time. In aircrafts, they have, let's say, just a hole somewhere here on the surface perpendicular to the flow that measures the static pressure, and for this one they have pitot tube to measure dynamic pressures. And these things basically gives you the velocity of the speed of the aircraft. Nowadays we have gadgetry like GPS and all this, but fundamentally these are the things which measures the pressure, and they already know what is the formula as we move up in altitude, what are the pressures, densities. So they have calibrated, they used to have calibration in such a way that the altimeter would know that how high we are in altitude, because they have a diaphragm which has, let's say, atmospheric pressure enclosed, and then you have an outlet which is the physical pressure at what altitude it is flying. So it measures that pressure, and it knows the atmospheric pressure in that diaphragm, so that expands or closes, and the meter kind of moves, which tells you that how high you are in altitude. So we'll discuss more on what is a static pressure and something known as a dynamic pressure, and means how are they related to the velocity is the Bernoulli equation, but in what sense, right? So last thing was, I told the other section, so let me tell you as well. The kind of questions which you would expect in the exams are true false, maybe 10 or 20 maybe. I think it's a couple of hours exam, I guess. 2 hours? 3? Okay.
11 to 1 p.m.
11 to, okay. So expect maybe 90 minutes or 2 hours questions. I am not sure, I have not made it yet. But true false is one. Short questions, some simple numericals, conceptual numericals. It's not just randomly that you, or maybe trivial kind of easy ones. And there might be some derivations, as I had asked in the quiz, that you should know what are the steps and what is the final conclusion, what are the assumptions, or what is necessary to derive this. I remember in one of the quiz I had asked about the pressure in like a triangle thing, something, or independent of direction, and somebody proved the next section with the Taylor series, right? So if I ask you that, show it to me that it is independent of the pressure, so you should be very much clear that what am I talking about, right? How to prove it. It's not that you just whatever you know just write it down. You should know which section or which derivation has what kind of conclusion. Okay, And true false, they will be coupled with a negative marking. So just don't go TFFT. Alright, make sure that you know it, then you mark it. So far so good? So I think there are no classes. Are there classes next week? Only papers? Next week? Oh, it's on Monday. Next Monday. So good luck, and I'll see you on the exam day. But if there is no policy which has come out till now for the next Thursday's class. Is it? No written policy? Just rumors? They won't be coming for the class?
Yes, sir.
I would be, so if there are classes, then I would be coming. Okay, so so don't worry about the units. You should be independent of the units. Okay, I'll give you all the required numbers. If there are none, elementary means some basic, because rest of the chapters which are coming in the book, which some of them we will cover in FM1. My goal in this class is go till chapter 5. We should finish chapter 5, and then chapter 6 onwards we should include it in FM2. So all those lucky guys who would make up for FM2 will cover 6, 7, 8 and 9 and blah blah blah. Right? The rest I'll see you next year, hopefully. Okay? But the point is that even if you go over while reading the book in chapter 3, you will see, oh, this will be covered later in 5.11.3. Right? So you will see some reference which are ahead in the book. Initially, some basic fundamental terminologies are introduced here, and based on that next coming chapters will cover the topic in detail. But anyways, we talked of certain things. The most important is Newton's second law. And why is that? Because of this, the word dynamics. Right? So there is a very interesting area on research which is known as CFD. How many of you know that? What is that? Right, so this is like computation. And this one is like fluid. And this one is dynamics. I might have mentioned it earlier, but all those who are really serious about learning or doing some future studies in CFD, they should better start from D. You should be good in D. Then you should know FD. And the last thing which you should focus on is C. It goes the other way. Because sometimes all those who would be interested in doing their final year project with some fluid analysis or turbines or blades, pumps, whatever. So the big chunk which is missing is the dynamics part, and then the fluid dynamics part. CFD is easy. You just need to click in a software, click. You get help from somebody, a friend of yours or some instructor, and then you are done. You see some figures, and the next question you ask, what do these represent? No clue. Right? Why? Because you do not understand the underlying dynamics or the fluid dynamics behind whatever is happening. So I would strongly urge you that, or rather motivate you in a way that all these subjects, although you go over them separately in your undergraduate studies, somehow that they are interconnected. And the link really comes from mathematics. If you have a good mathematical background, then these, nothing, simple. Acceleration is x double dot, so it's a second order equation. You can apply whatever you have learned in mathematics about second order equation, and you can solve for the forces. Good? Okay, so mathematically this is this. F equals ma. We give F as the force which might be coming from pressure, or it might be coming from gravitational force. Okay, so this is what it is, and on the right hand side we know that mass, which we would kindly ultimately write it in terms of density and volumes. So, and this one is A. Is this a vector equation or a scalar equation?
Vector.
Right, so that means we can decompose into different components. Excuse me. A traditional or conventional way of looking at things is x and y direction. But sometimes what happens is that if a fluid particle is going in, let's say in a circle, then r theta is a good component, or you can say those are the frame of references which you should be following, r and theta. Then if a particle is going in this radial direction, you can keep a track of it, that okay, theta is 0, theta is 45, 90 and so on. If you are talking of x and y, then things are changing rapidly in x and y. It is difficult for you to keep a track. Going in a circle means that radius is fixed. You don't have to worry about one axis, which is the r axis, and then theta is just changing. So now what you have done is you have reduced the problem from two coordinates x and y to r and theta. R is not changing, so you are only concerned with theta. That is why most of these transformations, they are done. Those transformations, x equals r cosine theta, y equals r sine theta. So this is some mathematical stuff, but they have some physical significance once you apply it to solve any problem. Good? So the next thing is that the fluid particle does not go in a straight line or does not go in a circle only. It is arbitrary. If I switch on the air conditioning unit, the fluid particle will come out and it would follow some crazy path, right? And that path which it follows, where the velocity vectors are always tangent. If it is at that moment it is heading in this direction, let's say if this is the particle, it is heading in this direction. After some time it is heading in this direction. After certain time it is heading in this direction. So these are the vectors, and for certain plot it might become the tangent vector, something like this. So now the path of this, or the streamline which it follows, if I join this, it may look like something like this. It may look something like, okay, or rather it should be kind of going like this. It's my bad. Something like this. Now this yellow line is basically the streamline. Why? Because the velocity vectors, they are tangent to this line, and this line is known as streamline. So what we have done is we have defined a line for a crazy particle who is moving right here and there, left and right, but that is moving based on some law. There is no such thing as random. Maybe from electrical engineer guys you'll say, oh, there are certain things which are random numbers. Let's say from our perspective, from a perspective of mechanical engineers, or let's say aerospace engineers, the point here is that things change from, or things evolve in time based on certain laws. Sometimes we know those laws and we call them Newton's law, Bernoulli's equations, Navier-Stokes equations, or any other law, any other equation you can think of, heat equation. So these are standard laws which, by virtue of experiments or observations, people know that this would happen. So people came up with those equations by doing experiments or some other by observing things. So they wrote those equations, and there are certain things even now which we do not know. How do they vary? All of a sudden there is a hurricane kind of build up and it is coming to the coast. Sometimes we have earthquakes and we have no clue why it happened, what law is governing the movement of the plates in the earth. So we call those kind of systems as sometimes chaotic, right? So we do not know how, or we do not know what principles are behind those things, or what are those equations which govern that this would happen. So sometimes we call that, oh, this is a chaotic system, we have no clue about it. But God knows that these are the things which are moving in a certain fashion. If we do not know it, that does not mean that it's all random. There are laws, but we have not reached till that point. Okay. So based on this, I want to cover is a very fundamental law, mostly covered in fluid mechanics, especially at undergraduate level. That is the very important thing or equation that is known as Bernoulli's equation. We will derive that Bernoulli's equation today, and we will see that once people started analyzing this guy, Daniel Bernoulli was in 1700s working on some fluid mechanics stuff. So in those times, once people started observing, they saw that river is flowing. If they put anything in the middle, it goes fast. Anything which is close to the river bank, that hardly moves. So there is some velocity variation along the width of the river. In the middle it is the fastest, and then towards the corner it is the slowest. Or sometimes, let's say, if this is the width of the river and this is the bank, so it is excuse me, it is maybe something like this. Okay, so somewhere in the middle region we say that okay, the water is flowing fast, and close to the banks it is slow, and very close it is almost zero. Nothing happens there. So now this part is generally known as boundary layer region. This part. Now if I tell you something, and this is based on observation, people did not know about it, but by just looking at the river they could see that okay, the central region has the maximum velocity and not at the edges. So in order to write the equation or how the pressure varies as the velocity is varying, they had no clue about those things in those times. So what they did was they assumed that everything is moving with this central velocity, as if there is no boundary layer. They just assumed it, because first they wanted to write equations that how this pressure volume velocity changes in this region. They found it, but how does this happen here remained a question mark till I think 1905. To write an equation to model boundary layer, so Blasius was the first guy who kind of wrote an analytical expression that okay, this is the law which is governs the boundary layer on flat plate. Similarly, if I give you an example that let's say this is a table in front of us, and if there is a fan here and it is blowing towards that, so the velocity variation over the table is something like this. To be honest, most of you will go crazy that what is this? What is this figure? But that point is that the particles which are very close to the table, they are moving slow, and as you go slightly up, they move fast. But the thickness of the boundary layer is maybe less than millimeters or in millimeters. That is very small. So back then in 1700s, people decided that okay, if we cannot write the equation of the boundary layer, forget about the boundary layer, write the equations for rest of the stuff, which is this middle part, or which is this bigger area, which is this part. At least we should know something about this. So this guy came up with an equation with certain assumptions, and we know that part as Bernoulli's equation. That is applicable only in this region. Only in this region. So there are certain assumptions in Bernoulli's equation, and by the end of the class I'll give some details or 3-4 points that these are the assumptions. So just do not expect them in the exam. They will be in the exam, not this one, since chapter 3 is not there, but they're part of the exam. If you don't know it, you lose points, or they might be part of a quiz. They are so important, because I've seen people standing doing their master's final defense, supposedly masters of this subject, and you ask them some basic fundamental question that does this work for this problem, and they would kind of falter. So some basic assumptions you should know, that these equations, they work under certain circumstances, not always. So those things are known as assumptions. Okay, let's come back to some mathy stuff in this fluid mechanics. That was just a motivation. By the way, this part was later done by Blasius back in 1905, and he came up with a nonlinear equation. Obviously, this is not a linear equation. It's not cannot be represented by a linear equation. So he came up with something which is known as a Blasius profile. This is a Blasius profile here, back in 1905, and he got really famous. So over a flat plate, the boundary layer follows a Blasius profile. And that's what he did in 1905. So before that part, people were just analyzing or studying this part, central part. Okay, so we already said that it's not always, the particles, they are not always moving in this direction, or let's say it's not a good circle. Let me draw it again, try it. Yeah, it's not just moving in circles, which is r and theta. It could move any arbitrary direction. So if this is the particle, and this line is drawn from the velocity tangent vectors, so we call this path as S, the streamline. So one coordinate is S, and the other coordinate is the normal to this, which is N. So this direction is S, and the other direction is N. So what we do is we consider S and N coordinates, let's say, and we follow this coordinates. This is the path which it would follow. So instead of kind of doing X and Y all the time, we said, okay, it would follow the streamline. That is one coordinate, and the other one is N coordinate. So just like even in dynamics, or in even statics, you decompose the forces in X and Y. In this, we would resolve the force in S and N directions, right? And in the beginning, I've said that what kind of forces are we expecting? One is coming from gravity, the other is pressure. So there are two things: pressure force and gravitational force. So let's kind of do some analysis, and by the time it is moving there are two kinds of accelerations involved, and that part I think we covered, AN and AS. One is along the streamlined acceleration, the other one is the normal component of it, and we had written this as this, AN as V square over R, radius of curvature. This is what it is. So we are first, just like in previous cases, we have X direction and then Y direction. First we will analyze F equals ma along S direction and then N direction. So let's first do it in F equals ma along a streamline. So sigma of F, delta F along streamline, this S subscript is streamline, is small variation in M and S, because delta is here as well, that's why I'm putting delta. What is mass in terms of density and volume? Okay, so rho is constant, let's say, or rho is the density. We have delta V, which is because of this delta, we have a delta here, and then we have acceleration as this. So this is the main Newton's law for a fluid particle in this direction.
Mass vary करेगा या acceleration?
The volume, both, right? Velocity is changing in s direction, but delta volume is the particle which you are looking at. It's going to be this one, that one. This is the volume. The density will not change. Okay, so this is delta Fs. So we said that there are two things which are happening. One, the force is coming from the weight, and that Ws will have two components if this is the case. Okay, so let's zoom in this picture and let me draw it here. This is that particle here, and the line is going something like this, and it's going something like this, and we have this. So this one is s direction and this one is n direction. This is the weight. Let's kind of if the weight is in this direction, okay, and this is all those who have books, please look at that. Otherwise, I strongly recommend that. I may not be able to draw a very good drawing, so please go back and look at your books as well. If this is theta, so that means this is theta. There are two components of the weights. One is this one and the other one is this one. So this one is in the streamline direction. And what is this? It is, what is weight basically? W is mass times gravity, right? Mass times gravity. What is M? Rho, let's say delta V, G. And what is G times rho? Okay, now this becomes like gamma thingy, and this is this direction. So what should, this is theta. So negative gamma delta V. This is along S, but in opposite direction. That is why the negative sign is there. Okay, now there is something very, very interesting, and I am assuming, maybe it's a wrong assumption, but this is pressure P here. There is something here. There is, let me use another color. Let's say we have yellow. Okay. Pink. Wow. But I hear a different kind of voice. I won't look up. Maybe it leaves a bad impression. Okay. Okay, anyways, it's good. It's the red point, okay. So now if you remember chapter 2, in the very beginning, there are certain derivations. If this picture is exactly like in X and Y, let me draw that thing for you. You have P here. Okay? Now what we did was we were able to, and this distance used to be delta x by 2, and we came up with an expression of delta px, delta p delta x, which was approximately equal to something. So we kind of said that this is p plus delta px, and this p minus delta px. Remember that? Does it? Excellent. I was not expecting it from you. So few people are serious in life. Either it is the motivation of Eid break or their series, yeah. Right? So if this figure is drawn like this horizontally, then you might know what I am doing. This was done previously. So let's come back to that convention. So this is kind of x direction and this is kind of y direction. Now nothing has happened other than I have tilted this fluid particle, and the two x's which I am talking about are s and n. That's about it. So what I should be looking at is now p plus delta of ps and p minus delta ps. This corresponds to this point and this corresponds to this point. And what I'm going to do now is write this expression directly, assuming that you guys know it, which is delta p sub s is approximately equal to partial p partial s delta s over 2. Previously it used to be delta p delta partial p partial x delta x over 2. In s direction this would be the total delta p between the two walls, the pressure differential. So between this place and this place, between these 2 points, you have this variation in pressure. Right. Chapter 2 stuff. Let me write it here. Chapter 2 stuff. And I would really appreciate if you go back and do this, because this is a good candidate to ask maybe in the final exam. So far so good? Okay. Go back. So now we said the forces are because of two things. One is the weight, the other is the pressure. This weight is already there. Now let's do it for the pressure. So the pressure okay, let me ask you this. I wrote weight and then I wrote delta W of S. For this small particle, this is the weight acting in the S direction. For pressure, can I write delta P sub S? Why is that? Right, pressure is scalar. So that is why I wrote F of P sub S. Whenever we are resolving the forces, we do not say that, oh, the components of the pressure are, no, absolutely wrong. The pressure force has components. And how do you get a force from a pressure? Force per unit area, right? F is P times the area. That gives you the force due to that pressure. So that is kind of maybe a nitty-gritty stuff, but a conceptual thing. And don't ever just resolve pressure into Px, Py, Pz. Right? So do not embarrass yourself, right? If you're talking high in terms of fluid mechanics. Simple thing, but conceptual. Okay, so P minus delta Ps, and you can look at in the books as well. In the book as well, I'll tell you what is y. If you remember, in chapter 2 we had 3 directions, x, y and z. We are saying that the fluid particle, which is S and N, the third direction into the wall or out of this wall is y direction. Just a convention. It could be anything else as well. Z, okay. But this is the convention in the book. Okay, equals minus 2 of delta PS, delta N, delta Y. Now this delta PS is we just wrote the value of this. That is why this FPS now becomes partial P, partial S, delta N, delta Y, and this thing is in fact all the three directions. So that is minus P, partial S over the volume. Now this is the force due to pressure in the streamline direction. Okay, this is the variation of the force in the streamline direction due to pressure. That is why FPS. Now if I have to write this complete sum of forces in the streamline direction, one is coming from the weight and the other one is coming from okay, why there is no this? Why there is no tau? Because in this we are considering inviscid, no viscosity. Because right in the beginning I said we are not concerned with the banks of the profile, river banks profile. We are just concentrating on the middle part. So there is no shearing between the layers. Everything is moving with the same velocity. So we are concentrating on the part which is in the middle. That's what it is. Good? Okay, so what is this? We have this written as minus gamma of what? Sine theta. And this one is written as, and there was a delta V as well. We had minus P delta V. And this thing is F equals MA basically. So we have to kind of consider the right hand side as well. Good? Okay. I'll write the right hand side right now in the next step. So unfortunately, I think I already mentioned that this part is not coming in the exam, so a few of the guys might be, oh, we'll see once it comes. Macho guys, right? Who cares, but it's not coming in on Monday 14th. So let's concentrate on chapter 1 and 2 and leave it to the end. Done? Next slide. Okay, so we have, I'm just going to write minus gamma of sine of theta. Nothing fancy, I'm just taking this delta V outside. And what was M times A? Rho delta V, and along the streamline was this. So this goes away. What does this mean? Right. So the volume is kind of arbitrary. There is something known as, maybe in UG level these things are not there, but arbitrary. If you are talking to a mathematics guy, he would maybe spend the whole class and cancelling this number. But why this delta V is cancelled? Why? Because the volume you are considering is arbitrary. The fluid particle could be of any kind of shape, or it could be any dimension. So he would come up with a theorem to prove that it is arbitrary. That's why you can ignore it. Okay. So as an engineers, we just kind of, come on, cross it, leave it. So far so good, right? Now what we have is a very interesting equation, minus sine of theta minus p partial s is, now what it has given you, the orientation of the fluid particle by sine of theta, the variation in pressure relates to the variation in the velocity field. Okay. So this is the physical significance, that how the pressure and the velocity, they are varying as it is moving along the streamline direction. Okay, so now let's go back to break. Okay. No, I might leave a little late. And there's a meeting scheduled, so I have to kind of prepare that. Anyways, this was S direction, this was N direction, and we had W component in this direction. This was theta, and we had this direction and that direction. Sorry? No. I'm still in S. I won't go anywhere. Okay, and we have this X and Z. Okay, we'll say that sine of theta is dz ds. This thing, right, because let me write this. Just hold on. Can you kind of visualize the situation? You have S and N changing, but like the global frame of reference is the same, X, Z and S, X, Y and Z. I said Y is coming out of the board, is going into the board. X is as given here, X is already this one. Z is this one, along which the gravity acts, because no matter how you tilt the body, it is always going to act in the Z direction, if these are the coordinates. That is why with the right hand rule, Y goes inwards inside the board, X and Y, that's why Z is up. So the weight is acting in the Z direction, but since we are doing S and N coordinates, that's why it is something like this. So this one is strictly in the Z direction. This is, let's say, d of Z, and this is d of S. Now sine theta can be written as the perpendicular over, the hypotenuse over perpendicular. Is this okay then? This is not correct? Okay, hold on. Let's say if I have this.
Sin theta is equal to opposite over hypotenuse. That would be.
So this one is ds, isn't it? So let's see. This is interesting. Sine of theta is okay, hold on. Let's, convention in the book is this one. This is the height Z, and this is theta, and this is S. If we copy paste this thing over here, does that work? How? Let's see. No. Then we might have a conventional issue. Undergraduate stuff, FSC stuff. Metric? Good. I guess so. Metric stuff. Yeah. Well, anyways, this is the dimensions, and theta is this. Am I doing the projection wrong? Which one is this one? This is theta. Oh, hold on. Maybe the x and z, they are wrong. The way it is given. Particle thickness is this one. Sahi? Are you sure? Anyways, let's follow the convention in the book. Let's follow the convention in the book. And because this, check this one as well. X dz ds, is this the convention? Right, this is the convention which is followed in the book. So we have to replace this thing here. The convention followed in the book. So this becomes, okay, and here is another thing. This is maths, which is, this is equal to half of rho dv square ds. Any doubts about this? If you open it, if you take this becomes 2 times v, because you are differentiating this, and whatever is inside you take dv ds, right? And then you have half there, that's why half cancels with this 2, and you have this. So 2 cancels and you are left with rho v dv ds. And there is a reason why we are doing it. Okay, let's write this again. The red is not the best color. Okay, it's kind of orangish.
सर एक्चुअली वो ना नॉट ट्रीटमेंट लेके पहले थीटा निकाला, फिर उसने कहा कि वो थीटा इसके इक्वल है.
ओके,
निकाला सर वो जो एस एक्स के साथ जो एंगल बना रहा है ना उससे निकाला.
okay, change it. Let's look at this one first, and then I'll see what conventions are followed in the book, because we just started writing x, y and z. Now this can be written as, because v is a function of s. What does this mean? Since we are looking only in the s direction, we say that v is a function of s. Now if I write it differently, a little different, is v s. Can I do this? Now what I want in my governing equation is that this s should be outside whatever comes inside. So that just like delta v or delta volume, we cancelled it. If I integrate the equation, let's say if you have anything like this, if you have anything like this, d over dx has anything, and I integrate, what do you get? A question mark. Because you know that just cancels. So that is why what we want here is that we want to take this somewhere outside. Just mathematical stuff. In order to cancel, or once we integrate, cancel this partial s. So what you do is you write this part as Now let's do it step by step. If you have to differentiate what is this? Or did I write it correctly, or x should be here? Okay, let's do that. 2x
dot dx by
dx. Okay. Now give me this. The half is already there.
partial b on partial
Oh yeah. Which half? Oh, in order to equate this, I have to write this half. Otherwise, this equation is not balanced. I have to cancel this too to bring this back. Crazy stuff, right? Because this guy was doing it back in 1700s. Right? He wanted to have one formulation. Now what I have slightly changed is I have made it a complete derivative. Why? We are looking only in along streamlines. Now if I integrate this equation, what happens? What cancels out? Now this is a complete sentence. Integrate along the streamline.
d over ds.
So I can do this. Where's the minus? Okay, yeah. Although this is not a good way to write it, because you don't have equal sign here. That's a not good way. But the point is just to get the point across. And skipping some steps here. Now this equation is known as so the physical significance of this equation is that it gives you a relationship between P, the pressure, the velocity field, and let's say if you are moving the fluid in a z direction. Right? If it is only moving in a straight line and there is no variation in the z direction, so there is no effect of this term, and we are talking of this. Let's say if in a pipe, something like this. So if there is a restriction or a tunneling effect or like a nozzle effect, so this pressure would decrease or increase? Decrease. Why? Because the velocity is increasing. and this is the law it would follow. So the question basically comes in, if the velocity increasing, how much variation is in the pressure field. So this is what happens, right? So these are the analysis done by this guy and a mathematical proof for a fluid particle, how it would behave if it is in this situation. But most importantly, there are certain assumptions which are in there. Okay, so once these assumptions are true, only then you can apply this equation. Some fundamental and the conceptual thing in this Bernoulli's equation is that you must know the assumptions. Okay. So let's meet after the break, like at 12 to 10. I'll take sorry, good, some okay, I'll take attendance at 12:10. It's 11:56 my time.